Hi, Carsten.
Hi.
Good afternoon. I'm very happy to proceed with my talk. I also look around the room. There's no hands raised, so I guess we're safe to proceed, Carsten.
Okay, thank you, Jan. Thank you, Alex.
Thank you. Thank you very much.
Excellent. Good afternoon, colleagues and guests. It's my pleasure to actually kick off the afternoon part of the showcase day. That is a series of academic presentations trying to go a little deeper, into the scientific outcome and advances we managed to accomplish in the Fair Space program. So I'm from the Surrey, part of the activity. So it's been a excellent journey for our team here. I just want to echo what Martin has mentioned in the morning, that there is a research program that put together for this consortium to conduct that include 5 different research themes. So in sensing, perception, mobility mechanism, navigation AI, human-robot interaction, and system engineering. Just so you know, we didn't come up with this just randomly. So there's a excellent documentation, which is a white paper co-created by industry academia, and this was sponsored by UK ROS network, on space robotics and autonomous systems, that has recognized these 5 cross-cutting themes. The reason they're called cross-cutting is because you will find their role to play in different space mission scenarios, or we call use cases, orbital, planetary surface, and astronaut robot interaction missions. So the part I'm presenting in my talk is looking at what Surrey's role is, because obviously the reason this is a collaborative and consortium activity is because, different academic part in this country can bring in different academic contributions. So for instance, one of the things that Surrey has been tasked to do and deliver looks at the research thing 1 and 3, that is the sensing, perception, navigation AI, and translate the scientific new knowledge into demonstration in orbital manipulation. It is worth highlighting the fact that, I'm sorry, is there a laser pointer with this back? Please, thank you. Maybe run out of battery, sorry. So if I can just draw your attention to the 2 pictures on the left-hand side. So you have on-orbit assembly, active debris removal. So these are the 2 very representative mission or use case scenarios for orbital manipulation, meaning you would, in those mission scenarios, rely on robotic manipulators to do the pick and place or capture retrieval. Of course, they deal with different targets because the OOA is dealing with cooperative targets, while the ADR deal with non-cooperative. So just to highlight the scientific backing in this research program. So here, this slide outlines the key scientific advances in developing monocular-based perception for post-estimation using deep learning. So we come up with 2 types of solutions within this kind of scientific approach. there is a non-key point based or direct approach that is using relatively simple software architecture based on ResNet. Is a CNN backbone architecture, then followed by 2 branches that does the estimation for both locational or orientational. As I said previously, we are ranked in the top of global ground challenges. So there is a confirmation where we stand in terms of international competitiveness. And you also have deep learning, but using key point based approaches. And this is complementary to the direct approach because it gives you a more scalable architecture, as shown on the figure on the right hand side, on the bottom here, which compared to the first direct approach that really allows you as an end user to exchange the different components. So for instance, with this particular problem we're addressing for space application, you need to detect the object of interest, the key point estimation, and use PMP and RANSAC to give you that post estimation, and also allows us to avoid overfitting with the training data. Obviously, we want your train network to be as generalizable as possible, isn't it? Because you would expect something you can't be fully capturing during the training phase. So that's very natural. It's an important design objective from the end user perspective. And of course, validation is critical in this case. So we done validations using many, possible, target data set. Some are real world space mission data set, which, for example, on the left-hand side of this slide, the speed data set, which has also been used by European Space Agency when they coordinate organized ground challenges. Well, on the right-hand side, you have synthetic data sets, and these are photorealistic ones that don't undermine the importance of synthetic data set, because they really can help us pick up things maybe sometime the real world data set might not fully represent the challenge. So for instance, the video playing here on the left-hand side, that's the real data set on the Soyuz from some of the NASA missions. Well, on the right-hand side of that video is showing what's rendered from our in-house orbit visual simulator, where we can introduce additional challenges when we test and validate our technique. Of course, we didn't stop there. You already showed live demo this morning about on the ADR scenario with a test bed. And similarly, we're doing that with the OOA, which is the on-orbit assembly scenario. So on the left, we go through the data sets that produce us very extensive trials. So we can pick up all the quite near realistic features from space. Well, on the right-hand side, which is played by a film captured from the runtime demo, where you show how the test bed we use for ADR can be repurposed in this case to demonstrate the OOA challenge. So you can see that on the left-hand side, the servicing arm, through visual guidance, to try to approach and dock with the target object. In this case is because this OOA is basically a mirror segment of a large space telescope, where you have pre-designed interlocking or interface system that would lock the two things together. And that's really a very interesting bit, where you can clearly see from the sub-window there, the vision system on board the servicing arm clearly lose over 50% of the target object, will still be able to proceed with the docking successfully. That is showcasing the benefit of using AI. Ooh, that's fast. So moving on, looking at some further research behind the technique. So here we're looking at Rgbd based perception. So meaning you have the bare minimum monocular vision, but only on top you have some very sparse, depth sensing capability, very sparse, as you can see from the point cloud picture there on the first row of the slides. Well, through our algorithm, looking at a zero moment shift, where you pick up really the surface region that are stable, and you segment it and cluster them, work out the places that according to the physics of your gripper that are realistic for you to go and grasp. So that whole data pipeline is autonomous and can work really fast because the minimalistic amount of data we use in real-time processing. And also the technique takes into consideration of stability analysis. And this is very important. Of course, as you can imagine, with two fingered gripper, that's a higher challenge. When you increase the number of gripper, the stability would be more guaranteed. So we start with the two-fingered because we know that represent probably the highest challenge when it comes to guarantee the stiffness, stability of that grasping action. So here you can see the technique we use, intrinsic stiffness matrix. Again, there's a heritage of that principle from the terrestrial robotics. So we're not completely reinventing the wheel because that's no point. And this was implemented quite successfully with our application. So here the asymmetrical stability potentially caused by the curvy surface, as well as the uneven kind of geometry from the inner and outer part of the object is what we have successfully tackled. Again, just to highlight our industry engagement. So here we're not just case the film play a demo we had in the innovation zone during the UK Space Conference, where we collaborated with a very successful British company called Shadow Robot Company. They specialize in making multi-fingered robotic hands. So as you can see, the end effector is now replaced by this multi-fingered hand from Shadow, and that's showing the same technique on the software side from us and how it's able to do that grasping even with all the colorful background. You can see the distractions you have in that demonstration hall. This is a good example of us using our expertise to help UK-based business to extend their potential applications and customer base from terrestrial to space sector. Another big chunk of work that Surrey has been tasked to do is looking at some really research investigation into SIM2. Let's look at mobility and mechanisms. So here, the use case that correspond to that scientific or research challenges is to do with planetary surface missions, again, I draw attention to the two images on the left-hand side that kind of put a picture or image around what sort of missions we're talking about. The, for example, the sample return missions or in situ resource utilization missions. I mean, you would appreciate from those, either artistic drawing for futuristic mission or some pictures reflecting ongoing interplanetary surface missions that it would involve surface vehicle. So these are mobile vehicle in the form of a rover or drilling instruments that need to deploy payloads that has to go subsurface or to help construct infrastructures, big infrastructures on planetary surfaces. It could be Mars or the Moon. So here, just to give you examples of our research, one of the key advances is in developing mobile active rover chassis with enhanced locomotion, or MACL in short. So what MACL can do, it really can allow a very compact micro rover chassis to deal with both rocky terrain as well as sandy terrain. So it could be, surface that is very rough, as well as you have a relative flat surface, but packed with loose sand. And this is actually very challenging for one design chassis to deal with. So here, it allows us to really think hard to develop a cell that can really offer, this final integrated design can do both. So there's some data about the actual physical size and weight on the slides, which you can pick up, but just to highlight how we do the trick here. So we have a vertical hinge joint that allow the rover to steal the body heading. And then I wonder whether the tech team can help me play the animated film on the slides. Because, yeah, thank you. So you can see that the work principle is to have only two actuation systems. One is a vertical joint, one is an angular zero elastic actuation. So one in front, one slightly on the back of the body that allows, the climbing behaviors as well as a crawling to be achieved using just these two actuators. Of course, this, I have to show you the actual physical prototype, and you can see, this was implemented in real world with worm geared motors, with some close-up pictures. And worth mentioning, the four wheels obviously also have their own motor, rotational motor, purely just to rotate the wheels. And also worth highlighting the fact there are some spiral springs that help to really implement that elastic actuation that is in our novel design. Just some further words about what's on board, just for testing purposes. Of course, not so much to add about computation there, but worth maybe highlighting the different sensors that has been used. So for the bogie, we have steering pivot and also the wheel motor, which is bulk standard, which is, nothing we're adding any complexity or difficulty or cost to what typically existing, just to show how this, this is close to the real implementation in in near or midterm missions. And there are also force and torque sensors allow us to get force feedback to implement the control, the gate control of the vehicle. So here I'm giving you, it's a very sensitive buttons here. So I might need my colleague in the tech team to help me ensure this is now playing. Can you help, the tech team can help me play that film there. Excellent. I think it's moving, isn't it? Is that moving or stopped again? If you, oh, excellent. So you can see how the crawling behavior with the coordination of the two motors can really help lift the rover up from the entrapment of loose sand. And both joints are basically doing its job. Well, the climbing capability is also a good showcase of the coordination between the two linear motors. And here, we also have force sensors to help give us the feedback that we can estimate the friction, so we know where the limits are. As you can see close up, that the rover is a very small in its size and in its footprint compared to that rock, a very rocky surface there, but is able to overcome something which is 2 times more, higher than the actual radius of that wheel we use in the demo. And moving on to the importance of subsurface mobility, obviously anybody who is going to fly some of the missions to Mars or the Moon, they're not only going to be just satisfied to have a surface mobility, they would need go to subsurface, either collect sample or in place scientific instruments to analyze. And you hear people talk about mining as well, and particularly there are a lot of commercial initiatives, but it is very, very challenging to sample in particularly microgravity environment. It could be asteroid, comets, or moon. I think relatively speaking, Mars is also a smaller body compared to us. So if you want to use a technique that we use on Earth to work at the same cost, that's probably not possible. So you have to look innovatively about new mechanisms for drilling. So this is the actual physical embodiment of the robot, not just software. So here we inspired by the wood wasp. So there's a photo of the famous wood wasp there, and the part that is circled by the red line is actually the part of the insect's body called ovipositor that is used by the insect to lay eggs in the wood. So this can, I think we've been told by biologists that some wood wasp, such as the Japanese wood wasp, can actually extend the ovipositor up to a number of meters for a body, from a body that is only as long as 1 centimeter. That's just incredible, because the reason it can do that, of course, all this little legs is trying to anchor on the tree, sure, but the reason it can extend that long versus its body size is because the drilling mechanism is not relying on any rotation. It's relying on dual reciprocation from 2 parts in that drill body, which is kind of illustrated by the design examples here at the bottom of the slide. So these are 2 halves with teeth features so that it can help, engage with the regulars, so that there will be a traction between the drill bit and the regulars. And this dual reciprocation would allow that traction to help the penetration rather than purely rely on the overhead weight. So this is the trick here for this kind of new drilling technique. So obviously, when we have to translate that biological prototype into an engineering prototype, we have to do so much testing in terms of the design that is suitable for engineering tool. So here you can see a few examples we designed for different regulus properties, soft soil, tough soil, or hard or soft rock. Here is just one system design that we come up with a demonstration goal in head within the lifetime of this project. So this looks at utilizing the dual reciprocation motion, which I mentioned or explained earlier, but also adding the lateral motion, because through our investigation, we found the lateral motion or vibration really help improve that performance. So here is giving you a zoom in of the design itself and how the dual reciprocation is implemented using DC motor and also cylindrical cam mechanism. And you can see the animation there, how it works. And similarly, giving you the information about how the lateral motion or vibration is achieved by a very simplistic design here using an inclined ridge, because we need to simplify design, try to minimize the complexity so that this is welcome by the space application. And of course, we have the actual hardware prototype, and all that photograph basically shows how they look like in reality, and the video showing how this is actually drilling into the regulus. And these are Martian simulants we use in our lab. Again, to highlight the fact we're engaging with industry as well for this part of the research. So the BT is the one we team up. So they have this extraordinarily interesting real-world problem in the utility sector where they need to deploy their fiber cable. And this needs to be deployed horizontally, not vertically, as I show for the Mars or Moon case. So what is very important is that we set up the test bed to allow that to be tested. And thanks to this mechanism, because it was with the idea in mind when we designed it to deal with low gravitational field, because we don't have much gravity to assist the penetration. And you can see the synergy here with horizontal drilling on Earth, because again, you're not getting that much gravitational assistance when you have to drill horizontally. So here you can see how that has been done. And similarly, we have the same test in BT's facility to confirm this is useful. So again, as a sort of summary here, that a lot of this has been published in a brand new book, thanks to IET. So feel free to grab a copy if you're interested to know the technical details. But I put this as my last slide before I finish off, because I've been asked by my colleagues to say a few words about, the future, looking forward, what should be the roadmap technologically and what we should focus. So I've been always saying in our space robotics community and our forums that in the long term, what really the industrial commercial world are looking at achieving is long-lived system, long-lived future generation of space systems, which has robust mobility, and autonomy. So to get to that long-term goal, we need some near and midterm kind of milestones, shall we say. So there are a number of key technical directions we have to continue to pursue. So that include low computational, high accuracy 3D mapping and perception. As you would appreciate, when you really want to use very controllable robotic mechanisms for those tasks, there is almost like a hidden objective there for accuracy and precision. And then there's also energy optimized locomotion mechanism, because we don't have the luxury of all the energy in the world. When you are in outer space or deep space, we have to be very resource aware when we design mechanisms and data processing, and also growingly introduction of artificial intelligence, machine learning into a lot of our navigation and control systems. We need to be fully aware of how to tune the data. It can't be a black box solution. It has to, we have to have the knowledge to verify in real time the solutions we present to the industry and users, and reconfigurability for both hardware and software are very needed. I think that, to my very last slide. Thank you very much. So are we moving to the next talk? So I have my colleague.
Alex. All right. Okay. So thank you very much for Yang's excellent presentation. Here's the presentation that I can elaborate a little bit more what happened behind the scene just now during the live demo. So me again here, Alex. I'm the assistant professor in robotics and control machine learning. So today's presentation here is from me and Professor Samir from Subsurface, and we'll talk about more in depth what is behind the scene in terms of technologies for this dexterous robotic manipulation, and what is the smart mechanism that we have designed in terms of intelligent gripper. So all of them sit in the context of variable autonomous teleoperation in space. And first, I would like to again recap what is the hub vision we have and what's our ambition. So we'll briefly go through the capability we have demonstrated, but most importantly, I would like to highlight, so what's next? So we have done a great job in terms of bringing all the technology together to achieve such complicated and challenging tasks in a remote setting. So what is more beyond this hub, right? So I'd like to elaborate a little bit more futuristic research that has been going on, and then I will conclude the session by the future vision. So if we look at the recent decade, there have been great research and engineering work which has been done in the space section by various funding agencies. So they have developed very good technology in terms of pre-programmed automated solutions that happens on the robot side, and human operators can operate through the space from the spacecraft in the orbit. So that has been demonstrated very, very recent years in terms of this teleoperation capabilities. However, if you look at the robot autonomy, it's still limited to pre-programmed behaviors. So the level of autonomy can be further improved, as we demonstrated in our live demo. And furthermore, how to really team up humans and robots together in order to really cover a wide range of tasks and applications as much as possible. So in that context, it's clear that we demonstrate that's the ambition from this hub, and we have how we push these capabilities beyond the state of the art. So as you have seen all these real robot, real world demonstrations and capabilities, we see there's a huge potential how those technologies can be further transferred if we can work together in the next few years or decades. We'll bring this technology into a much better readiness and to using the space industry, such as lunar gateway and pre-deployment in Mars. And as you have seen already in the lab demos, so we are able to achieve in presence of latency such complicated dexterous manipulation of space assembly, as well as a fine manipulation for the inspection of power units and exchange of the power units as well. So here is the simple snapshot of what has happened. I just recap that the top row shows how the robots can do autonomous acquisition of a moving object. So that technology can be used for space assembly as well as debris removal. And the bottom is the case where the humans can really parachuting embody themselves in the robot through our multi-modal interface and operational modes in order to achieve very, very dexterous and fine manipulation. So here is a little bit more graphic view to illustrate how this has been done at the background. So as you can see here, so this is a clear view of graphics to show you that the human operator is arbitrarily commanding the green box here. So there's arbitrary commands coming from human side while using teleoperation mode. So anything can possibly go wrong in this regard, and not all the commanded motions can be safely and reliably executed. So the software is, we have developed most cutting edge software to enable those computational efficient real-time filtering that running on the robot in order to adapt any incoming reference into feasible motions that is safe to execute. So as you can see here, the robot wouldn't really overstretch out of the workspace, and in terms of rotation, it will understand it's carrying a heavy object, and the blue arrow is the forces and etc. As you can see here, the robot wouldn't lose the grip and wouldn't lose the object. And in terms of such in the context of the shared control here. So this is the technology happening behind it. So most of the capabilities have been demonstrated, and the basic principles and fundamental rules have been explained already. And here I would like to take this chance to explain more what's the next, what are the futuristic research we can do, and that can really, as taking all these results as a pathway in order to reach more realistic and feasible application in space. So as you can see here, we have developed a very nice interface and system that glues humans and robots together. So as you can see, the teleoperation runs very well and achieve the feasible operation of physical tasks. And in between that, because we have full control of the interface, we stream all this data flow in due ways. So this is bilateral teleoperation, and we are able to record and collect our data as time goes by. So this data comes for free as long as we keep the teleoperation running. So as time goes by, we are enriching and increasing the database. And from this database and demonstrations happening there, as you can see, we can observe. So the machine, the AI can observe how what humans do and how humans do it. And from all this data, we are able to learn those humans, the motor skills from humans, and in order to enable all these autonomous behaviors. So here, as you can see, it's fully automated object grasping and from human demonstrations. So everything, all the AI, as you see here, uses the real data to learn this autonomous grasping behavior. So there's no human programming, manual coding at all. It's purely done by observing. So looking at the data and observing how humans do it. So as you may notice, that left, right hands are slightly asymmetric. So those also learned as well when humans operate and then grasp the object. So the AI can transfer the human skills. The learning algorithm can transfer the human skills from a skilled operator to machines seamlessly. So everything is done by real data. So previously, as you have seen in the demo, it's done through the teleoperation in terms of docking and space assembly. And here I will let the video play one more time.
Auto docking activated.
So as you may notice, you can hear the click sound, right? So here what's happening behind it is that by observing human demonstrations, so we are able to mine the data and find out the features such as changes, forces, and together with its configuration, let's say position, for example. And from all these features, the AI can understand that you should push and dock the object until the force has a step change, and that's the moment to stop pushing it. And all this requires no programming, no manual coding, but simply by streaming all this teleoperation data. So this is the autonomous docking learned from the real data. So this is the mixed autonomy, which is very similar to what you have seen before. So basically, it's a slightly different teleoperation using different end effector, just to show that the similar space assembly tasks can be also used as well using completely different end effector. So here again, the second run, this is autonomous mode. It's repeatable and reliable. And once you grasp it, human can take over smoothly using hybrid control mode in order to achieve. So as you can see here, we are able to do space assembly and docking in both autonomous mode or teleoperation mode. So there's a full range of flexibility to combine both. Okay, so the next is interesting showcase about more complicated teleoperation, as we briefly mentioned in the previous question and answer. So some of you might have the experience in terms of the drilling. So you know that to drill it's not trivial. If the first time you try it, you may break the drill, because to sense the interaction force is important. If you twist it, you might break the drill. So that showcases and demonstrates the advantages of our both physical and virtual and graphical operation interfaces that allow us to do to complete such challenging tasks such as drilling. And in this way, we are able to deploy the robot in the space or outside of the space craft without the need of having space work. We can deploy robots to do that. So you might know that Canadian Arm has been doing similar space repair and maintenance jobs, and we are really looking at the next level of capabilities that offers much better dexterity. So here is another example to show the inspection. So as we said before, the inspection and space servicing can happen in orbit, and we might as well using exactly the same technology for the planetary services and whatever tasks that needs to be done on the ground surface. So they can happen either in the Mars surface and lunar surfaces or on the ground, as in construction and other sectors as well, or disaster response. So here I will hand to Professor Samir to talk about the design of the intelligent gripper.
The gripper we developed in this project is inspired by nature, which provides a robust and active grasp control system for unknown grasp scenarios, with the capability of dealing with uncertainties and stochastic disturbances. The characteristic of this controller is that it optimizes the grasp force by detecting object edges and its movement to firmly grip the objects and prevent their slippage. Grasping unknown objects in unknown cluttered environments is one of the main features of this gripper. This is in addition to its mechanical design, which offers dexterity. These features are all highly desirable in space and other hazardous environments. Future development of this gripper would involve integration of further economical and resilient sensors to increase its autonomy, speed, and adaptability. Considering a scenario, for example, that represented teleoperation of robotics arms to perform certain tasks, such as object manipulation and by manual operation in space, then a specific novel end effector had to be designed to satisfy the numerous constraints, such as limited payload, for example, range, robustness, and stability of grasp. Then the technical novelties of the proposed gripper are, first, we propose a novel hybrid soft-rigid design to develop a bio-inspired dexterous four-fingered gripper. This gripper is capable of pinching and grasping simultaneously and is directly inspired by the motion and architecture of a biological hand, which consists of rigid bones. In our case, we use the carbon fiber, and also enveloping muscle tissues and cartilages. And in our case, we use a thermoplastic polyurethane in our design. The second significant novelty of this design lies in its capability to easily grasp and prevent slippage of both delicate as well as hard, heavy object with the help of its hybrid soft-rigid structure. Furthermore, then the novel dual tendon actuation system implemented in this design facilitates configurability and a flat surface grasping capability. Pinching action without the addition of an extra actuator, hence then the weight, resilience, and dynamics are all optimized in the manufacturing process. The third innovation of the proposed gripper is its ability to detect and avoid object slippage. This feature facilitates stable grasping and manipulation of objects while preventing breakdown, damaging of the object grasped. Slip avoidance is achieved by computation-efficient algorithm as well, based on luminance differencing. Computation efficiency of this algorithm facilitates deployment and autonomous control of this gripper on just a single ARM-based processor. Then, apart from the main challenges addressed by the smart gripper, it additionally boasts of space-crucial features such as a weight with sub-kilograms, and modularity. We have seen it, then it can operate with 2, 3, or 4 fingers. This is an example video of the optic processing where the algorithm intelligently converts monocular cue into a simple edge and depth information used to perceive the incoming object in 3D. Now, this video demonstrates the dexterity and stability of the grasping by the smart gripper in 4-finger configuration. Then up next, modularity of the gripper is showcased here to illustrate its capability to function effectively even in 2-fingered configuration. The relationship between motor's phase rotation decides the direction of finger movements. An adaptive force control design here for the gripper prevents grasp-induced damage to objects grasped. Then, irrespective of object thickness, the variable grasping range on this gripper facilitates manipulation of a wide range of objects. As we can see here, testing of the smart gripper is taken one step further by attempting to grasp and manipulate larger and heavier objects, such as the CubeSat, as you can see in this video, and a mock-up nozzle presented previously in the ADR demonstration. Microgravity is simulated by suspending the objects mid-air, which led to a successful manipulation by the proposed gripper.
All right, so thank you very much for Samir's presentation. So Sami has explained very well the technical innovation we have done within Hub, and particularly from Suffolk University. And here you can see how the smart grapper has been nicely integrated into the teleoperation system in order to achieve successful teleoperation remotely from London. So that ranges, that covers the wide range of innovation, including software, interfaces, hardware, and so on. And looking beyond, so as we can see here, those capabilities has been tested heavily in the lab for more than a year and has demonstrated very good reliability and repeatability for various tasks, as you can see here. So this can achieve space assembly docking, and also the services such as inspection and exchange of power hose, power units, and etc. And looking into the future, in particular, I have elaborated more what has been done most lately to translate all these technologies into the next stage, which is to use the learning method. So as we know that the power consumption of the learning of the neural chip is very, very low, and that is particularly suited for space application where the power, the energy is very limited. So looking into the future, all this demonstration, the videos you have seen before, shows a great potential that a lot of those technologies can be further pushed forward in terms of using the AI and the neural chips that is very, very low, has very, very low power consumptions, and that gives us a huge leverage in terms of deploying these technologies in the real world scenario for long and short distance, long and short range servicing in space. And moreover, as you can see, that it has been demonstrated repetitively, successfully in the lab, the readiness level, we can push further the readiness level and generate more useful applications in other industry sectors, such as healthcare, construction, rescue, disaster response, and so on. And this can generate much more societal impact and benefits. So if you look at the exchange of power hose, it's not only useful for space, but if you look at the future need of self-driving cars, to how to charge all these electric batteries autonomously in the future, fully electric power stations, such technologies of inspecting all these power hoses and changes can be also deployed for this sector as well. And that potentially really can generate a huge revenue for the future economy and create much more values. And so with that said, I would like to conclude my presentation and give my sincere big thank you to all these excellent researchers who has done the fantastic job, particularly during the live demo. Right, so I think we're in time.
Very much.
So I will hand over to the Carsten.
Thank you, Alex.
So the next we have the coffee break. And so the current session concludes at 5 to 3, and we will have a short, let's say, 15 minutes break. I'm Carsten. Okay. All right. So
thank you.
Let's have a.
Thank you, Alex. Yes. So if we break now, and then after the coffee break in 15 minutes, we'll hear from Etienne, who's with me here in Imperial, and Claire Dixon, who's also here. So we will see you in 15 minutes. Thank you.
Yeah.
Do we need to start again? Do we need to start again?
Okay, yeah.
I start? Okay. But there is no. but you don't see anything. Okay. Okay, so my name is Etienne Burdet, so I will present some of the activity we do in the context of the Space project at Imperial College. So first, I would like to present the lab we are working in. This is this human interface lab. So involving 4 faculties. So the first one is Majid, who is actually here, working on soft robotics. Second, there is Dario Farina, who is working on neural interfacing, especially signal processing for EMG and also EEG and other modalities. Juan Gallego is working on computational neuroscience and brain-computer interface. And with my group, we are working on human robotics, so robotics to understand human and to help human, and augmentation. So so these are some of the companies we work with. So our goals, so we want to develop disruptive approaches for interaction, augmentation, and restoration. So to help people increasing their abilities or compensating for the lack of ability. We want to work also, we work on the scientific aspect and also on applied aspects, so developing the technology. And we have translation. So for example, with these companies, so we are working with these companies in Singapore. So this is kind of a spin-off of the lab. We have been working with Star Motion, and with this is also a spin-off of the lab. Just an example of, I would say, a next project. So we want to work on a framework, on a versatile environment. So to make to develop very many applications. So one would be for space technology, actually. So if you have augmentation to supernomy robotics arm, so you could work by yourself on holding something. So for example, you hold something to screw something, you assemble part. For that you need more than your arm, and we work on the control of such supernomy mechanism. We could develop multi-limb rehabilitation involving both the lower limb and the upper limb. That is a new tendency in neural rehabilitation. Maintenance tasks, so to train maintenance tasks. For example, in this fusion reactor, you have heard that recently in the UK there has been a very big advances in fusion technology. And finally, for hand surgery, so hand surgeon, surgical robots like the Da Vinci that you can see in the demonstration room have 4 different manipulators, and right now you need several people, so you need the surgeon and an assistant to actuate this robot. But if you could do everything by yourself, you would not need you would not have the possible cooperation problem. You would need to learn only to work with your forelimb, but not to work with every new assistant. Okay, so this is just an illustration. Now to come back to what we have done in this project. So this is what was presented. So this demonstration of teleoperation where Imperial is at the Earth station and Edinburgh would be, for example, at the ISS. And we have been investigating direct teleoperation, so like Aran demonstrated. And so we are interested in developing further shared strategies. So as Carsten was mentioning, for example, we are interested in understanding how 2 people work together and how this works when one is here and one is there, so with a delay. Okay, so the goal generally is to replace or collaborate with an astronaut from the Earth. We need to develop the teleoperation between the Earth station and the ISS, considering typical delay time. So Earth to the ISS, 30 milliseconds, what is actually not very long. But to the moon, it is 6 seconds, so completely different. In the addition, you have, of course, possible signal disruptions, so things that we have to test. And we wanted to understand how does the delay influence interaction control. So we investigated in several ways, and we want to develop basically a robust interaction control for teleoperation. So we based on experiments that we did. So this is when you have two people working in contacts, for example, to manipulate to manipulate an object together. And what we have found previously is that when you collaborate with something like that, maybe exchanging forces to an object or directly, then you make a model of the partner so that you can get the sensor information of the partner. So you can get your eyes and the eyes of the partner, and so improve your manipulation ability. Now, we wanted to test that the effect of delay between these two people. So what we used is that we have a robot partner that is a model of how the human is interacting. We have tested this model previously. And so we want to put a delay, different delay between a human and this robotic partner. And okay, so this is the effect of delay. So you can see that, so different delay time, you see that the error is not increasing much until more than 100 milliseconds, so 180, then you have an increase. And you see if you measure the muscle co-contraction, that muscle co-contraction is increasing from 60, so perhaps to compensate. Now, when we asked to the people how they felt, so whether they felt resistance or whether they felt an interaction, we see that even in 20 milliseconds, they are quite aware of a delay. So they are quite aware of a delay, but are able to compensate until more than 100. And we have developed a computational model to understand and to be able to simulate the effect of this delay. So it seems that subjects model explicitly the delay and are able to compensate for this delay like with a Kalman filter in a way. And okay, so as experiment we have done, this has been presented very briefly by Alex. So we have done experiment with the simulator of the Canada arm, measuring EEG and also eye movement, so to detect where you are looking and whether your attention is still there or not. Measuring physiological signal with devices developed by Panos, as you can see on the posters. So this is a video of what is happening. So you have to consider debris. You have to pick something and to place it with this Canada arm, and you have these 4 cameras. And so you have these 4 cameras that give you different feedback so that you can carry out this operation. And we measure the number of collision, time cost, the precision, the docking precision, and we estimate the workloads with different latency, time delay, and with time pressure. And so we have done several studies. This is published, but I show you the recording. So you have simultaneous recording of EEG, gaze, and the movement. So this is experiments that have been done here in Amlin, actually several years ago now, and so all these results are published, and it had basically estimation of workload, so technique to estimate workload both from EEG or from eye gaze. Okay. Another thing we have been doing is to develop a soft exoskeleton to make training of the astronauts during the flight. Regine has developed a novel technique based on cable to measure, so like our tendon, and also to actuate the body. And so some of these are demonstrated in the posters, and I can show you also more of the results there. And this is all for my presentation about some of the studies we did. So I would like to thank, so Alex thanks the people for the teleoperation. I would like to do it again because collaboration went very well. So with Kunta and Alex in Edinburgh, and on the Imperial side, so Ahan and Ziwei and Katja. Thank you.
We propose solutions to effectively monitor astronauts' state and assistance to mitigate their physical and mental load. Good afternoon, ladies and gentlemen. My name is Samia Niftimaziani. I am Professor of Robotics and Artificial Intelligence. I'm pleased to present the work that my team has been working on. It's related to scalable modular soft glove. I'm conscious about the time allocated to this presentation, therefore I will try to be as brief as possible. I will try briefly to describe first the objective of the project and give some summary of the different achievements so far. The concept behind the teleoperation use case involves human-robot and human-human interaction mediated by machines. The scenarios involving human-robot interactions deals with wearable robot integrated into a spacesuit and the autonomy shared between astronauts and space robots. For this project, then, we propose solutions to effectively monitor astronauts' state and assistance to mitigate their physical and mental load. With the introduction of novel soft sensor on the wearable gloves and suits, wearer states identification is performed and fed back into the control system to augment astronauts' intentions. States such as pressure points is in the form of a matrix is measured using e-textile picking up resistance difference across palm of the glove wearer. This video then shows a graph-based feedback picked up by a soft sensor sleeve that can facilitate augmentation of wearer's intentions when used in combination with an efficient actuation system. A precise sensor characterization is performed to identify the effective structure and layers of e-textile required to prepare a functional soft sensing glove palm. Main advantages of this then process includes easing of future maintenance and reducing the end cost of manufacturing as the structure and number of textile layers are optimized. Now this video shows a force augmentation glove prototype that uses the extensor bending pneumatic muscle actuator. Then this actuator is used to form a hand exoskeleton to assist the bending of finger joints to perform multiple gripping and pinching movements. When pressurized, the pneumatic muscle bend and in turn apply a force to the user's fingers to amplify the power of the hand. This video illustrates human-robot interaction where the astronaut's mental and physical load is mitigated with the help of an AI-powered system, recognizing and translating simple gestures into complex tasks performed by the machine.
This is gesture recognition with the operator wearing haptic glove. This is the move away function, recognized the object moving away. And now we have come here function, recognized visually with the object moving towards the operator. And now the haptic feedback, the operator touching the object and the vibrators producing vibration on the operator's glove.
Future development and integration of the presented technological solution in the Fair Space Hub could result in highly advanced wearable suit capable not only at improving haptic sensing, but also augmenting intentions and physical responses of the astronaut, all of which strive then to mitigate the physical as well as the mental load exerted on an astronaut. Additionally, this solution can successfully be extended to other sectors, such as nuclear, for example, nuclear decommissioning, that also operates in hazardous environments.
Thanks for sticking it out this far. I'm Claire Dixon. I'm from the University of Manchester, and I'm going to talk about what we're doing on theme 5, I think it was, which was systems engineering. I've got a chunk of time, followed by Carsten, and possibly we've got the panel next. I'm doing my thanks at first. So that's the team. We started when we were on Fair Space originally at the University of Liverpool. Quite a few of us moved to the University of Manchester, and you can see some of the team moved other places. So we've moved to Aberdeen, Maynooth University. Some people stayed at Liverpool and Liverpool John Moores University. So thanks to the rest of the team. This was joint work, partly with Warwick, and we also worked with Yang's team at Surrey. So space robotics, lots of issues there that we've talked about all day, during the day. So things like remoteness, danger, communication delays, contamination, extreme conditions. If something breaks, we can't easily get to the moon or Mars to go and fix things. Environments, we know a certain amount, but there's a lot of uncertainty about there. You know, if things break down, what do we do? Is there, you know, do the robots have good recovery from failure? Often the environments may change. They may be unknown. They are very hazardous. And the other issue that was mentioned this morning in the session with Martin was we might need these robots to work in close collaboration with astronauts, with humans in general. It might be via teleoperation, that we've just seen from the demonstration. It might be actually there with an astronaut. So the other thing that we were very interested in at Liverpool, then Manchester, was autonomy. And again, that was mentioned in the session this morning. You know, more autonomy seems to be the future of space robotics, in my opinion. So the robots may have to make decisions. They may have to choose between alternatives and make the best decision between those alternatives without any interactions from humans. So the key thing that the Liverpool and then Manchester team were interested in is, how do they make those decisions? How do they make them so the robots react in a safe way? And they do what they're supposed to do, and the astronauts and the other systems around them can trust those robotics. So I'm going to have a few slides on our sort of techniques that we use to do this, and then I'm going to whiz through some of the mini projects we did as part of this theme. So the first thing that we're particularly interested in is verification and validation. So what is that? Well, usually if you want something doing, if you want some space robotics, you go and ask the stakeholders, what do they actually need? What do we need doing? Then there's often some requirements, the system's designed and then it's constructed. So what verification is doing, it's checking whether the design satisfies those requirements. It's checking whether the system we built satisfies the design and those requirements. And it's often captured by the words, are we building the system right? So validation is often, are we building the right system? So we're involving the stakeholders. Is the system, the design and the specification, what those stakeholders actually wanted us to do? So I'm more on the verification side. The team looked more at verification than validation. So techniques that we're going to use are things like formal verification. So that's a mathematical analysis of systems. We look at, this is an exhaustive approach, so we look at all runs through the system, but often you have to take an abstraction of that system. And we use tools and techniques such as model checking and theorem proving. I won't have time to tell you what those things are, but I'll bandy those words around in the slides that are coming up. We also use non-formal techniques, things like software testing, things like simulation-based testing. So if we've got space robotics, it's really difficult to send our things into space to check that they work. So we might build a simulation and run tests through that simulation to check things work as expected. And finally, physical testing. Well, yeah, we could send things into space, but hopefully we'll be able to try and test things on Earth in a closer environment as we're going to use those. And for instance, we had earlier on, I think it was in Yang's talk, when she had some sand and a rover trying to get out of the sand and move over an obstacle. For validation, often things like physical testing, you know, like you saw with Yang, we've got users there and we've got test scenarios to run through. So why do we need to do verification and validation? You saw lots of space robotics. We saw, picking things up. We saw moving over obstacles, lots of things you've seen today. We want to do things beyond that. We want to make sure that these robots operate as they should do, that they do what they're supposed to do. We want to make sure that they're safe, that, a robot arm picking something up doesn't turn around to the astronaut and, hit the astronaut. We want to make sure that the robots are reliable, that they don't break down all the time. We want to make sure they're robust. So if they did break down, can we work around that? Is there something else we could do to achieve the mission? Similarly with reconfigurability, is there another robot gripper we could use? Or with Etienne's, the thing with all the arms there, can we use one of those other arms to do what we need? We need to know what the system's doing. You've told the rover to go and look at a piece of soil over there, and it's going back to the habitat. It needs to explain to the astronaut why it's not following your instructions. We've seen some discussion about security and attacks so far, and Carsten's going to say a bit more. But how secure is the system? Can it be hacked? And also, following on from the initial discussion this morning, we need to work with regulators. Can we make sure these systems are certified so we can actually take them to space? So here, more of the techniques. Design for verification. You should be thinking about verification before you start constructing your system. So top left, we've got an example of modularity. Break the system down into modular components. So if something goes wrong, we can swap into another component. But from the verification perspective, that we can verify individual components and put those verification results together. The one at the top right is saying, and I had a discussion with someone over lunch in relation to this, we'd like to separate out the low-level control with the high-level decision-making, the autonomous parts. So we can do a lot of verification, formal verification, other methods of verification on that high-level decision-making and, leave the low-level components with perhaps some testing. The one on the bottom left is, can we use different verification types together? So can we use formal verification? Can we use simulation-based testing and end-user experiments to improve the verification all round? So can we use outputs from, say, simulation-based testing to help our verification, the formal verification? Can we use it to guide those end-user experiments? So using these in conjunction to improve our verification assets and results. And last but not least, again, some modular verification. We were calling this heterogeneous verification. We'll need to use different verification types on different systems. So I think there we've got an example of a vision system, and probably we want to do software verification there. We've got a planning system, and we'd like to do some formal verification of that. We want to verify the different components using different suitable techniques and put those verification techniques together to verify the system as a whole. So this is some of the projects we were looking at. So the first one you've seen already, it's joint with the University of Surrey. It was a contribution to the active debris removal use case, and the pictures at the bottom you've seen with, we were trying to grasp a piece of debris there. So the big box on the top left that you can't see is some requirements. So we worked with the team at Surrey and we looked at what requirements were needed for this piece of software. One of the things was to make the best grab possible. Kind of sounds obvious, but it was one of the things that we specified as part of the requirements. And on the top right of that diagram then is a tool called the FRET tool, used as part of NASA to help specify those requirements formally. So we did this along with Yang's team, and then we did some formal verification of those requirements. And in particular, the one we've talked about, was satisfied. The requirement, the formal verification was done with a theorem prover called Daphne. The other thing that Yang did allude to in her presentation was doing some runtime verification. I've got another slide on runtime verification coming up, but it was also applied to this particular use case, so I'll say a bit more when the slide comes up. Next project was to do with autonomy, and as we heard this morning, we saw the future of space robotics needs more autonomy to be used here. So this was looking at the Mars Curiosity rover. You can download the software if you want to have a look at the Mars Curiosity rover. The software comes with a teleoperated mode. What we did was create an intelligent agent to do some autonomous decision making here. We used a waypoint scenario, and we did some verification of this using the Agent Java Pathfinder. That's a tool, model checking tool developed at the University of Liverpool and then Manchester. So what that funny formula is at the bottom, the box means always. So it's saying it's always the case that if the rover agent moves to waypoint X, then at some time in the future, the rover agent believes that they will be patrolling the waypoint X. So we did some verification of that to show that the agent was doing the right thing. Runtime verification. So Yang mentioned this in her presentation. So the idea with runtime verification, it happens when the robot is operating rather than before it's operating. So you've got a stream of data coming along, and you've got some I don't know, formulae, some patterns that you want to check for. There might be good things that you want to ensure are happening, or there might be bad things that you want to take action if something bad happens. You know, maybe if the battery's running low, you want to do something. So what we did, again, we looked at a rover scenario. We also applied this to the Surrey grasping algorithm, and we were monitoring certain properties. So what was developed by the Liverpool-Manchester team was this thing called the ROS monitoring runtime verification framework. And what that involves is it works on the ROS operating system, a robot operating system. What this does is it looks for messages between nodes on particular topics of interest and checks them against these formal properties that we want to raise a flag or take action if we detect something. This was also mentioned during the initial session, so increased human-robot interaction. So what we did here, we looked at documentation from NASA for, actions a robot might be interested in on something like, a moon village scenario. The robot would have to walk about with the rover. The robot would tell the rover, go and inspect that rock over there, take a sample over here, go back to the habitat, this type of interaction. So what we did was model this using Brahms. So this is an agent modeling language that was developed first at NASA. We did some verification of various properties that should hold for this scenario. And we did some proof and model checking using the SPIN model checker. Last one was some, penultimate one was some joint work with NASA. So one of our team was funded by FairSpace to go on a secondment to NASA. So this is the outcome of the work of that. And the idea here was, I've mentioned various formal verification tools. It was trying to create a system to use those different formal verification tools together in an assurance scenario. So a big diagram there. The tools that we used was FRET. So this was the thing that we mentioned before that was formalizing requirements. CocoSim, that's a verifications a tool for Simulink documents, and Event B. So those were all put together with this Advocate assurance case tool that is used at NASA to do a verification of a whole system. Two more to go. As we've just talked so far about, astronauts with single rovers or rovers doing things, we probably want to look at multiple rovers, multiple robot systems. So this might be swarms, it might be constellations, it might be platoons. So we're interested in how these can work together to achieve certain tasks. So lots of rovers, lots of satellites all working together. And we've looked at modeling these using a particular type of logic, first order temporal logic, and you know, trying to prove properties about groups of robot swarms. I think I've got two more still. I keep saying two more. I forget my slides. Again, relating to the discussion with Martin this morning, Martin and the panel there were talking about working with regulators. So as part of the team has helped develop standards, those are listed on there, IEEE and BSI standards. We've been working on development of standards. We've been working with regulators in other domains as well. And we think this is key to get these, you know, to get assurance of space robotic systems and make sure they're, you know, suitable and we can take them to space. Last, which leads into Carsten's talk, we've worked with the University of Warwick on combining verification with security, trying to create models that work for both of them. And this was a autonomous docking scenario. And I'll conclude, and then I don't have to come back after Carsten. So my concluding remarks, think of design for verification before you build the system. Requirements are important. We need to know what the system should do. We can use a whole bunch of different techniques together to improve verification, and we've been calling that corroborative verification. We can use different verification methodologies and tools on different parts of the software. And I think we should also look to other domains that have also been mentioned to help improve space robotics and the verification for that. Challenges and roadmaps for the future. We need more autonomy. How do we verify systems that learn? Someone mentioned reinforcement learning and learning before. They're really hard to verify apart from doing testing. We need to link better with standards and regulators. Issues with trustworthy. Some systems aren't trusted and some are over-trusted. Design, we need to work on better toolkits so we can enable roboticists to design and develop and verify systems themselves. We've got issues with environments, uncertain, unknown environments, and with formal verification, we have issues with the state space explosion. Thanks again for the team. Thanks to our funders. A few image credits there for all the images I've got, and I think I'm passing over to Carsten.
Thanks so much, Claire. I thought you were going to have two more slides then, but okay. So I'm the final speaker, I believe. I'll try to be quick, but I will show that slide again that you showed about security-minded verification. One thing is that the team at Warwick, we're recognized as an EPSRC NCSC Academic Center of Excellence in Cybersecurity Research. And this project, looking at space systems, really is part of that Academic Center of Excellence. So this is work done by a whole team of us. I won't list everybody's name, but I am just the spokesperson for the hard work that the rest of the team have done. And they've published various works and in conferences and in leading journals. But what we're really interested in is how do we engineer secure and resilient systems for space? And this is the thing that's important. A lot of people in the UK and around the world, academics, will talk about security, but it's not just around security. It's about trustworthiness, a term that Claire used a few times. And for us, part of that trustworthiness is resilience. Kieran Martin, who was the director of NCSC a little while ago, said in 2016, effectively he said, it's not if you'll be hacked, it's when you'll be hacked. We know that there's challenges in space systems. So one thing is it's not a new thing to hack systems. So we all are pretty much really a little bit used to systems being hacked, like a website being down, be it talk, being hacked for data or other kinds of attacks. But actually, there's been attacks on space systems for a really long time. At least one of these, can't remember which one, is from like close to 20 years ago. Some of them are more recent. This Visser, that's a parts manufacturer for Tesla and SpaceX, has had a data breach. And I mentioned before about how it could be in the supply chain that there are errors introduced, so some bugs. So we've seen lots of problems. This one here, Texas students hacked GPS. So GPS has been hacked a number of times. It's quite easy to spoof GPS. We actually did some intelligent jamming of GPS signals in a way that the receiver couldn't detect it was being jammed. And actually that led to autonomous vehicles crashing. So yeah, people have hacked sites for a long time. We heard this morning from people at the UKSA, the UK Space Agency, and they've got some responsibility at looking and making sure that space is secure. And they're interested in knowing what are the range of impacts of attack. What is does the type of mission affect impact? And how does the engineering infrastructure and concept of operations affect impact? So there's some of the questions that they're interested in. The European Space Agency, so funded through some work called Resilient Space Systems in Fair Space. We engaged with the European Space Agency and we got follow-on funding, working with various industry and academic groups to develop systems for secure space systems. But one of the first things that we did in space systems was to consider how do we do the risk management. This is a problem. Risk management is not easy, actually, because the first thing you need to do is assess a risk. And that's very difficult because sometimes, especially with a cyber risk, you don't know because you've no previous history sometimes. An attack could be the first time that it's seen. And you then need to understand what's the impact. So we developed a risk management process, building upon best practice from other areas, and published that about 4 years ago now. We then looked at a term that you've heard Dan talk about, commercialization of space. So the term new space has been used a lot. And we considered how does this, this commercialization of space, this complete change in the way that space is no longer restricted to nation states, but many companies going up and doing communications in space, or the kinds of course, we've got space tourism now. In fact, at the University of Warwick, we've sent up at least 3 CubeSats ourselves. And you saw some CubeSat grabbing from the Salford team before. So what we did is we looked at what are the differences between the communications infrastructure, so the so-called Internet of Space Things. Where is the change in autonomy? So Claire mentioned how autonomy is going to be important. And how is the change in the culture of this new space? So we looked at what changes because of different elements. So for example, cost of deployment has decreased because of the communications, but massively decreased because we're using commodity systems, so off-the-shelf systems for new space applications. We also considered in this new space environment the so-called threat modeling of space systems. So I mentioned a little earlier, if you were here for that we looked at the types of attackers, the threat actors. So you've got some individuals, and they may be outsiders, so they may be an individual, nothing to do with the space mission that you're on, or it might be an insider, yeah? So an insider might be somebody in your supply chain, for example, or it could be a trusted insider or privileged insider. These are people with different rights, and depending upon their rights means how much they can compromise a system and with what ease. So we looked at the threat actors, we looked at the examples about what motivated them, yeah, or what kind of people they were. So you've got so-called hacktivists, for example. You've got contractors. What they were trying to achieve, the goals and motivations, their capabilities. So how capable were they? So obviously, if you've got somebody who's a privileged insider, a serious engineer or employee, they will have strong capabilities because they work in this area. We looked at the environment, and we looked at the resources that they might have. So this helps us consider what are the most important things, because we can't consider everything. To help us, we used an idea that we'd used in other areas as well, including smart homes and connected autonomous vehicles. And we developed these reference architectures. So these are a high-level view of how a space system works. So this is the functional viewpoint of satellites. It's the reference architecture. So what you can do is when you have this, you can consider specific use cases and put them on top. So you instantiate this reference architecture, and then you can use that instantiation to find out what kind of attacks there might be. So we considered a whole range of these reference architectures. So this is robots in space. We looked at the ground segment that we've heard of before. And what we did is we built these so-called attack trees. So you can see here, what's the goal? So there's to prevent autonomous debris collection was one of the things. And how would you achieve that? How would you attack? So which part would you do? Which part of the attack surface? Claire mentioned this security-minded verification. So I'll just tell you briefly about that. So one of the things was, if you were looking at, you heard Yang talk about cooperative docking before, right? So if you've got some cooperative objects, that's one thing. But we talked about anti-cooperative. And what that means is actually that you've got something that could be cooperative, but it's been compromised. And what it's trying to do now is deliberately not create this docking. And what happens is if you just do the verification, yeah, then that's super. But you then need to think about how might someone compromise it. And then you have to do this threat modeling. Well, if you keep doing it, when you change a system to combat a threat, you need to re-verify. And this system, and using that example of autonomous docking, we went through and verified once we'd considered the threat. And the threat was that somebody might try to deplete the energy in one of your systems, so your element that was trying to dock, by compromising the other object. And these were the stages. So we looked at the different stages and where that attack would be compromised. And here again, you see a little bit of these threat actors that we're looking at in the threat modeling. I mentioned about resilience being more important than security. So the way that we define resilience is that we need to build systems that can detect, understand, and react and recover from a problem. And this is work we're doing in a number of areas at the moment. So what we want to do is increase the probability of detection, understanding, and act quickly. But also what we want to do is make sure that we don't have, if you have a Tesla at the moment, or a Jaguar Land Rover, or any other car that has got a machine vision system, if somebody compromises that machine vision system, they've compromised all vehicles of that type, because they are all engineered the same way. So what we're working on is engineering significant differences so that a compromise will only affect a certain proportion. So what we're doing is reducing the impact. So that's back to that risk assessment that we're doing. I mentioned the ResiSpace project and the work we're doing also with SSE for space, Secure Systems Engineering for Space, where we've worked with the European Space Agency to look at what recommendations are needed and what standards are needed to engineer secure systems. So what we found is a number of gaps in the software development processes around security requirements templates, the threat and risk assessment activities and processes, and others such as documentation deficiencies, for example. And we made some recommendation about what was required. And we're looking at the different tools that can support this. So actually, the tools are fairly haphazard, not all coordinated. So it leads to big problems. And Claire was saying just before about even that verification, about with verification and assurance, was bringing together, I think, 4 different tools. And that should be a lot easier and a lot more coordinated if we want to make sure that there are no holes in what we do. That's it from me. I don't know if I stuck to time. Probably not. I've gone over. I apologize. We'll hand over, I think, Sir Martin Sweeting is there. Martin, are you in Surrey? Can you hear us? Martin, can you hear us in Surrey?
I'm muted.
Ah, super.
Somebody needs to unmute me in the tick box.
We can hear you now, Martin.
Okay, good. Thank you. Right. Well, welcome to the Q&A session. First of all, I'd just like to thank all of the presenters and the demonstrators for the very interesting sessions this afternoon, and actually for keeping pretty well to time. And I have to say, I don't have 2 more slides. So with that, we're now going to have a Q&A session. I have a screen with some questions here, but I want to check that we have both Alex and Carsten and your crew available to answer the questions as they come up and contribute to them. So whilst I read these, is there anybody in here at Surrey got any questions, first of all? Yes, if you can just say your name as well when you ask the question, and then.
Hi, my name's Kit from the MTC. Thank you to Surrey University and everybody today for some really fantastic presentations today, so thank you. My question is, while there's this very dynamic situation with our UK spaceports coming online, potentially, they're going to be very, very hungry for business in the future. So I'm going to ask the question, how can we link the whole ecosystem from academics through to research and through to commercialization to feed those spaceports? And any thoughts about that, particularly in the areas of robotics and on all the areas we talked about today?
Right. Well, I'll attempt to answer that because it's a very, very broad question. I think the spaceports, of course, are going to provide access to orbit. So they are essentially the London bus that gets us from A to B. They are agnostic largely in terms of what payloads they're going to carry, but they are an enabling transport facility. I think the vision, and if I can perhaps speak on behalf of UKSA remotely, the vision is, and government, is that this will stimulate the space economy in the UK by having a national route to orbit, and that will provide greater opportunities to develop applications for orbit. So I'm not sure that it's going to be particularly linked to robotics, but in a much wider sense, I think we will just see it will stimulate the opportunities. Hopefully, that will stimulate the opportunities in the academic community and in the industrial community, but not just the industrial community, also what I might call the business community, because all of this is going to have to be financed, and not all of that finance will come from government. A lot of it is expected to come from the private sector. So clearly there's going to be a cooperation between all three. But any of my colleagues want to add anything to that?
One thing maybe I want to respond to Kate's question, because I think it's very important question, because I know Kate yourself is working on supply chain and trying to help support the community, put different technology component together. I just want to, recognize the importance of your efforts from MTC on that, and by saying me or my team as a potential solution provider to some building blocks of that supply chain. we would like to see some consolidation of the supply chain, which would give the community a better understanding of how things are connected, probably from the technological perspective, but also commercial perspective, so that potential contributors can see their potential roles in that overall roadmap. So I think that activity you've been doing and contributing is really invaluable. So we'd like to see maybe a further extension of that and see how solution providers can come on board and help implement some of that work.
Yeah, thank you. We've got quite a lot of questions, so let's quickly run through and give everybody an opportunity. From Praveen Kumar, the question is, what kind of regulation is going to be needed, if any, to provide a meaningful boost to space-based services, such as cleaning space debris, given that space is a bit like the Wild West and a coordinated approach is necessary? Anybody on the remote panel want to address that one? If not, again, this is a rather generic.
Claire has her hands
okay,
up.
sorry, you're not terribly clear, so you really have to wave wildly. Claire, over to you. Apologies.
Very short answer. Lots, I think. I think it's an area we need to look at more.
No, we can't hear you yet.
Okay, I'm thinking, continuing speaking, just in case that helps our tech teams here. Oh, and get some feedback as well. Continuing speaking in case it helps us.
Can you hear us, Martin?
Sorry, I'm afraid, Claire, we didn't hear any of that.
Can you hear me now?
Keep talking for your
Handheld. Oh, I was on there.
Oh, that's
better. Yeah. Okay. So I'm just up at the. I've moved location. So it's a very short answer. I think we need a lot of regulation, and I think with Carsten talked about new space. I think commercialization of space. I think it needs to be sort of thought out what we're putting up there, what the standards are, how we're going to regulate it. I don't have all those answers, but I think this is a big and important area so we don't have future disasters waiting for us. Thanks, that's me.
I think that it's not actually totally the Wild West, to be honest, because there is quite a regime of regulation that's applied, but it varies across the technologies. There's a very strict regime for satellite communications, slightly less strict regime for Earth observation, and then when we get down to things like space debris removal, those regimes are being developed. But there's a lot of activity in the United Nations, in particular, to develop these regulations and codes of practice for responsible behavior in space. The trick here is to make sure that there is sufficient regulation to prevent irresponsible behavior, and yet not so constrained regulation that it stifles the development of the space economy. And that balance is always a difficult one to get, and usually it errs on the side of conservatism and then slowly gets relaxed, but we'll have to see how that develops. The next question from Chatterjee Tekram. Okay, I'll let him, from Chatterjee, right. How open is Fair Space and the UK Space, or the UK Space Agency, to collaborate and work with international players to develop and commercialize new space technologies? Over to the other team first, Carsten and Co.
So I think that's a really good question. I think it's really important. I was thinking with the earlier question about from Kit, who mentioned about how we coordinate. And I think that is absolutely vital. And the academics in Fair Space are very committed to working together. We have to understand that working together will make the opportunities much more profitable and much more quickly. So I think it requires collaboration across international borders. It requires collaborations from academics, industry, and governments working together with regulators to make sure that we have this coordinated approach, and it's surprising to see, you know, where nations are in space strategies. So the UK only just recently having its own space strategy, which is surprising. And what we need to do is make sure that we look at the international landscape. So in answer to that question from Chatterjee, certainly the academics and the partners, I think you've seen throughout the day about how we're collaborating with industry. I've mentioned organizations such as ESA. Claire's mentioned about collaborations with NASA. And we're working with universities across the world. So some of the work that we've developed was developed with Johns Hopkins University in a recent paper. So yes, we're very keen on that.
Thanks, Carsten. There's a lot of questions, so there are one or two which are rather specific academic technical questions, which I suggest are taken offline if you'd like to direct that to the right groupings. But again, you have to forgive me because the name pronunciations, I'm sure, I'm going to make a hash of them. But Ugur Atamaka. So thanks for a fascinating demonstration. It's really good. But we'd like to understand about the communications delay between Edinburgh and Imperial. Was that representative of the sort of delays you would get in between ground and space?
Alex?
So Martin, I'm happy to take over the question. So could you repeat what is exactly the element between the Edinburgh and Imperial you mentioned?
Okay, Alex, it's a question of, was the latency between Imperial and Edinburgh typical of that you'd experience in space?
Okay, latency. So that's a very good question. So we have done the latency study. Basically, it's more work has been carried out in Imperial. So let me answer the question in two aspects. One is that what we found out that our teleoperation system for the remote and distance servicing can tolerate the delay from typically 40 milliseconds to 60 milliseconds and etc. without impeding too much of the performance. And it can go as much as about 100 milliseconds, which is 0.1 second. So beyond that, that can be more noticeable from human operator point of view, and that can start to have a little bit more pressure and stress on the human side. So with that said, if we look at the affordable latency at the 40 millisecond to 60 millisecond scale, and the cable internet communication now we have is within this limit. So at the moment, I can't recall the specific number, but the delay we have at the moment should be within this 40 millisecond, or that should be less than 40 to 60 millisecond scale. With that said, as you can see, despite obviously in terms of visual feedback and haptic feedback, there definitely were some latencies, but our operators in Imperial can still complete the mission successfully. Yeah.
Thank you. Sorry.
So, Quentin, do you have some numbers, specific numbers in terms of latency? If you can add on.
Yes. So we were using a direct internet link, so we had below 20 milliseconds of delay to them. But of course, for actual space communication, for example, between the ground and the ISS, it depends on your communication link. So if you have a direct link, as Etienne said, it's around 30 milliseconds. If you're using geosynchronous orbit relay, it's about 800 milliseconds. So the whole point of the demonstration was to add this shared autonomy control with some part of autonomous system and support of teleoperation to reduce the mental load. And this part are actually very important when we increase the latency, because this specific part get more difficult for the operator. At the same time, in part of the project, we conducted a few months ago with Kaja and other colleagues at Imperial user studies. So we had around 20 participants who went in Edinburgh and tested the system with various latency. And we are still studying the delay, but we show that even with high amount of delay, up to 1 second, they were still able to operate the system in a very similar tasks that were demonstrated today. So the system, thanks to this mental load monitoring and the specific parts that are carried out by the autonomous part, can handle large delay, such that space-to-ground latency.
Yeah. Thank you very much. So to simply wrap up the key numbers, the one you have seen during demo should be around 20 milliseconds, which is below the 40 to 60 millisecond scale. And for the nominal in-orbit servicing, given that distance, the delay should be around 40 milliseconds, which is still affordable. Of course, when we talk about extremely long range cross from Earth and Mars, then the delay is beyond the application scope. Thank you, Martin.
Thank you, Alex and Etienne. And of course, the delays to low Earth orbit aren't too bad, but when we're talking about going to the moon, then we will have very significant latency. Right, the next question, which is rather an interesting one, is from Anonymous, which I can pronounce. The grippers are like human hands, those that have been demonstrated. Is this accepted to be the best design for grasping, or are there other configurations? I.e., would 10 fingers or even tentacles be a model that we might pursue? I guess Samia would be the best person on that, perhaps, but I'm not sure if she's there. Anybody care to comment on that?
Hi, Professor. Can you hear me?
Yes, we can.
All right. I'm Hamid Isafani. I'm the research fellow at the University of Salford. I worked for Fair Space as a research fellow, responsible for developing the grippers. So to answer that question, of course, we've got different configurations of grippers. We've got soft grippers, rigid grippers, and there were a number of studies and exhaustive literature review on different solutions available. And the solutions that we came up and proposed for Fair Space were, of course, the two types, the rigid gripper as well as the soft gripper. The soft gripper was used for the teleoperation, and the rigid gripper was used for the ADR stream A of the project. So, of course, there are different, even other configurations of grippers, different types out there that are being used every day. And as the presentations explained, different presentations today, they explain different solutions. We could definitely look at other solutions as well and integrate them into the project according to the application. But as far as the applications that we were looking at, the rigid for the ADR was really compliant, and for the soft gripper was compliant for the teleoperation, and the adaptability and the reconfigurability of the gripper was very much advantageous for the teleoperation use case.
There are some.
Go ahead.
Yeah. So there's some additional information I can provide in terms of capability part, is that if you look at the mechanism design, so if you look at the grasping, basically there's three types of main synergies for all the daily tasks, and power grasp being one of the most essential ones. So particularly for debris removal or grasping a building block for space assembly is something that is of primary interest and importance. And with that said, if you look at the mechanism that has been developed by Salford, it is very clever in terms of its building the synergies into the mechanism. If you recall the material, it's very, very lightweight, and it's very, very light. So the payload is low for the space application. You can launch it, and it uses minimal number of actuators. So you really take advantage of the lightweight design, low payload, and the small number of actuators that can carry out the same level of dexterity and the compliance and adaptation to a wide range of different shapes and sizes. So that increased the feasibility of the real world applications.
Thank you, Alex. And another question which is interesting: will teleoperation be made redundant with increased autonomy?
Martin.
Sorry,
Could
Alex,
you
you
repeat
go
that
first
again?
if you would like to take this one as a start. Sorry. Okay, I can start and then hopefully others can follow. I don't think it will, because if you look at even from the ECSS standard, which is the standardization that the space community use, at least from the European community, is that the autonomy is always defined in different levels. So that range from remote operation up to the full level of autonomy. That standardization already demonstrates the fact different level autonomy is always relevant and required at different space scenarios. So there will be missions. I think the remote operation is deemed cost-effective, reliable, but then will always also be missions. I think we've seen very good examples like those deep space missions where we call full autonomy, which means you only set a mission level goal to the robots where the robot would make all sorts of decisions to achieve that mission goal. And that is also important to have when you have communication latency, or you have an environment that you really is completely exploratory, meaning you have no prior knowledge to safeguard the spacecraft. So the short answer is no, because we need all the level of autonomies to cope with different scenarios.
Yeah, I mean, I think it's a very good example of that is the JPL lander on Mars, where you have a very long latency of minutes, tens of minutes, and you have to have autonomy to adapt as the lander was coming in. But Alex, I think you were going to say something.
Okay, so
I hand over to Etienne, please. I think Yang has covered all what I want to say.
Etienne?
Thank you.
Okay, so what I want to say is that especially for the kind of task you have in space, I don't think you can make it automatic. Most of the tasks you cannot. Now, what we can develop, and that's what we are working on, is that you have techniques to much better understand the motion intention of the people, so that you can put some part autonomy or part assistance. And so if you are able to better detect what the people want to do, then you can also develop strategies to compensate for, not compensate, but cope with delay and still have successful operation. But typically the operation, so actually it's not only for space, all kind of maintenance tasks, it's very unlikely that you can do this easily with robots. And so in such case, so in space, it may not be possible to do with anything else than human, but even on the Earth, even in industry, in many cases, you might be able to develop some robot to do the task, but it would cost too much. It would not be flexible enough. So then, yeah, so in all this situation, the human cannot be replaced. Now again, so what we have to do is techniques to better understand what the human want to do and so assist the human more.
Thank you, Etienne. We're right down to the last couple of minutes, so I'd like to just ask each of the remote sites if they have any questions from the audiences there. So Alex, is there anybody in your audience that would like to ask a question?
And then a question from this side? Not at the moment.
And Carsten and gang?
Hi, Martin. I think we've all submitted them, but is there anyone here with any question that they'd like to ask? Or comment?
Yeah.
No, we're fine from Imperial, Martin.
Okay, I'm going to ask anybody here have any questions? No, resound. Oh, yes, we have one question. Right, just one minute, wait for the microphone.
Hi, yeah, I'm Abhinav Chabra, and I wanted to know, like, I've read some articles, like there's a increasing and collisions in the orbits are getting placed, like satellites are increasing, like SpaceX have put so many satellites, and another internet providers are also putting thousands of satellites in next coming years. So what are the approaches that we are following to so the satellite won't collide with each other? So is there any solutions to that, or ADR is the only solution?
Okay, I'll make a short answer and then I'll pass it over to perhaps Carsten and Co if they have a comment. I mean, the so-called mega constellations that are being launched now for primarily communications, which certainly already amount to thousands of satellites and may in due course get to tens of thousands of satellites. This is obviously increasing the population in space compared to the amount of debris, which is in the millions, depending on the size of the debris. It's still a relatively small contribution to the overall population. However, the danger occurs when if any one of those were either to collide and generate thousands of fragments or to spontaneously break up, as sometimes might happen if fuel eats through and causes an explosion. So the potential risk is there. There's certainly now, I'm aware, that there are close encounter warnings between the various satellites and existing spacecraft, which used to be in the order of once every month or two, are now happening almost every day. And that's when two space objects come within 100 meters of each other, and we have to decide whether there should be any maneuvers. So the risk has definitely increased. The mitigation is to ensure that, first of all, the spacecraft are not likely to explode, is the thing. In other words, you passivate the contents of the spacecraft as soon as possible. At the end of life, you deorbit them so that they don't remain in orbit and represent a hazard and they burn up in the atmosphere, or go out to a safe orbit. And then finally, if we get satellites that fail, which cannot be deorbited, then that is the commercial opportunity for the companies like ClearSpace and Astroscale, which are looking at commercial active space debris removal. So those are the main sort of aspects that we have to sort of consider. But let me put it over to Carsten and Co if you have anything to add to that.
Well, I think you've answered quite well, Martin, and especially because of the time constraints. But I think what is important is that communication and collaboration. The problem is there's so much stuff going up into space at the minute. We need to be really clear on who is responsible for that, and having this longevity, because now it's so cheap to put up, for example, CubeSats, put things into low Earth orbit. It becomes a problem about having that long record of who is responsible for it, and having that space debris managed. And that's why active debris removal is such a big issue at the moment, I think, for many organizations, nations.
If this works, regulation and guidelines come in again.
Yeah.
And in this case, autonomy.
Autonomy.
Yeah, so to complete to complete what I have told before, we have to create devices and test algorithms to make autonomous avoidance, of course, and removal of debris. Yeah.
Thank you. And I think there's one element that we sometimes overlook, and that is we need to understand what is in orbit and what is its behavior. In other words, what is sometimes called space situational awareness or space domain awareness. We need to be aware of what's up there, what is it doing, and where is it maneuvering, if it is going to maneuver, so that we can examine any potential risks of collision or other risks, so that we mitigate those results. Well, we're now just a moment or two over our allotted period, so thank you everybody for contributing these questions, and for everybody, Yang and colleagues remotely for their contributions to the answer. And that sort of brings us to the end. And I'd like to make just a few closing remarks, which I'm going to jump off here and move over here so we can shunt the camera around for a moment. I mean, first of all, thank you to all the presenters who've done a marvelous job. This is bringing today's event to a close. And I want to thank everybody who's contributed, all the research teams, of course, the government and industry supporters, the hub team that have helped put all this together, and their support from our technical teams who have made all this work and made the logistics of the event, and of course the summit that we had a month ago, and of course last but not least, all of those that have joined us online today, either as contributors or those that have been listening. This showcase today marks essentially the conclusion of the 5-year FairSpace Hub, which comes to a formal end at the end of this month in 2 weeks' time, and our money runs out. So that's a pretty good way to end. However, FairSpace has really provided, I hope, a really strong platform for the next phase of space robotics and autonomous systems, and I believe that this is going to fundamentally change how we operate and use space by the end of this decade. So this is not something that's going to happen in 2050 or whatever. By the end of this decade, by 2030, I think we will see the way we approach space change quite fundamentally. The way we operate in space, the way we use space, whether it be through in-orbit servicing, which we've heard a bit about, space debris removal, which we've discussed in some detail, in-orbit assembly, and we've seen examples of the work that FairSpace has done preparing for in-orbit assembly. And in-orbit assembly is going to be really important if we're going to build the next generation of James Webb Space Telescope, which we won't be able to pack into a rocket. It's going to be too big if we want to make it another step change. For space power generation, we're going to have solar arrays that are a square kilometer in size in orbit. You're not going to be able to launch those in a rocket. So we're going to have in-orbit assembly. And of course, beyond that, the holy grail, if you like, is going to be in-orbit manufacturing, because when we can launch a 3D printer, put a bag of sand, of silicon into the rocket and a chunk of metal, and ask the 3D printer to manufacture. I'm making it a bit simple, of course, but to then manufacture the spacecraft in orbit, we then relieve ourselves of the violent 20 minutes of being launched from Earth into orbit. And then once you're in orbit, satellites just sort of float around. If we can manufacture them in orbit, we can make them like a spider's web, very, very thin, very, very fragile by terrestrial standards, but very large. And that allows us to do things that currently are just not possible. I mentioned a little bit earlier in the discussion, the Royal Society is looking at 2050 and seeing what space might look like in 2050, so that governments and the general public can sort of be thinking about what sort of implications space in 2050 might have on our society. But I think robotics is something that's going to accelerate in the next 5, 6, 7 years quite dramatically. And so we were just discussing earlier today how we might bring this community together, because there are a number of different initiatives around the country looking at space robotics. How could we get a coherent approach and make sure that we have a joined up a discussion across the industrial, the academic and the government communities, so that the UK has a sort of coherent strategy. And of course, this fits very nicely into the recently announced UK National Space Strategy. As this is our sort of final event of FairSpace, I'd like to thank personally all the PIs that have led the teams, Yang, Claire, Carsten, Alex, Samir, and all their teams, and Etienne. Sorry, Etienne, I forgot you. All the teams that are behind them who have done contributed to FairSpace. I want to thank them, for their excellence, academic excellence, very hard work, and challenging times with COVID, and of course their support in bringing all this together and focus through the FairSpace hub. I would like to give a personal thanks both to Samia and Carsten in particular, who have helped me in the last year or so, and particularly for each of them who have led Samia the summit and Carsten on this event. And I want to thank them for their contributions. And of course, I want to thank the management team here, the hub team at Surrey, who have managed all the logistics and all the administrative issues over the years of FairSpace, and have supported not just, of course, the people at Surrey, but the other teams across the hub. As I said earlier, I think FairSpace has established a really strong UK community of excellence in robotics and autonomous systems for space across academia and industry. And our task now is to build upon that, so that the UK can play a key international role in what is going to be a really exciting decade ahead in terms of space exploration and space exploitation. And as we see what has been currently called new space, which has generated this tremendous activity in the private sector for space, develop into what we put here as next space. And next space is going to be very strongly involving space robotics, and developing economies in orbit and the lunar economy, both in terms of the lunar surface and the supporting infrastructure. And we need to make sure that the UK, we won't be able to lead that whole program, but there will be elements within those big programs where we have real expertise in academia and industry and business to play a strong international role, so that we can bring the benefits of the lunar economy and others, off-planet economies, as they're often called, to the UK. So with that, I'd like to close today's event. Thank you, everybody, for coming, participating, contributing, helping to organize it, and of course, for the last 5 years of work with FairSpace. So I hope that everybody in the various regions has got themselves organized for a little reception. We have a little informal reception here, which we will continue just to have a chat amongst ourselves. But thank you very much indeed.